Okay, so the idea that you just, use one big language model for absolutely everything you do online, that's fading fast. We're really diving headfirst into a world with lots of different models, and knowing how to pick the right one for each specific job, that's becoming super critical. This whole system for making that choice, deciding which model gets which task, that's what we call LLM routing.
Yeah.
But the way we've been doing routing, it has some pretty big problems. They tend to be inflexible, kind of slow, and honestly, they often pick the wrong model because they're stuck on academic scores instead of what, a person actually wants. So our mission today is a deep dive into something new, a framework called preference-aligned routing. It uses this surprisingly small 1.5 billion parameter model called Router, and the claim is, well, it fixes these core issues. All right, let's dig in. Before we jump to the fix, let's really understand the problem. We keep hearing about models with high MMLU scores or GPQA scores, these big academic benchmarks. They're supposed to be the best, right? So why shouldn't a router just aim for the highest score?
Yeah, that's exactly the point of tension. Older routing systems did mostly focus on those numbers, and that became their main limitation, leading to, well, basically two big kinds of failures when you actually try to use them. First, there's this mismatch between objective scores and subjective needs. Sure, a high MMLU score might mean a model is good at, say, multiple choice questions, but that tells you nothing about whether it's good for your specific task. Maybe you want really creative, snappy marketing text from one model, but for summarizing complex legal documents, you need a different one. Maybe one that's actually weaker on those standard tests, but nails the legal jargon. If the router only sees the scores, it ignores what you actually prefer, the tone, the style, the specific job you need done. It just picks the high score. And second, those older systems, they were just incredibly rigid, really limited in scope. They were usually trained as fixed classifiers on a tiny set of models, maybe just 3, maybe 10 specific LLMs. So if a fantastic new model dropped next week, or you needed to route for a totally new kind of task, forget it. You'd have to completely retrain the whole router, maybe even change its fundamental architecture just to add one new option. Super costly, super slow.
Okay, so we need something that lets me, the user, define what good means for my task, not just rely on a benchmark score. How does this Router thing actually capture that that's subjective human preference?
This is where the new framework gets really interesting. It fundamentally changes how you think about the problem. Instead of just, taking a query and spitting out a model name in one go, they break it down. They see it as aligning with preference, and they decouple the decision into 2 clear stages. First stage, the Router model looks at the user's query, the conversation history, and selects what they call a route policy. This policy is something the user defines in plain language, like use the best model for summarizing financial reports.
Yep.
Then second stage, there's a separate mapping, they call it T, that takes the chosen policy and assigns the specific model the user actually prefers for that policy.
Ah, okay. So the main router, the Router model itself, isn't directly picking the final LLM. It's just figuring out the intent or the policy needed. That does sound way more flexible. Why didn't older systems do that?
Well, the older systems were often built as classifiers, right? And when you build a classifier, the sort of natural, easy thing is to train it to output the final class label directly, in this case, the model ID. By splitting it, Router gets that flexibility and, importantly, transparency we were just talking about. And how users define these policies is also key. They use this structure called the Domain-Action Taxonomy. Pretty straightforward, really. The domain is the broad topic area, think like legal stuff, finance, healthcare, maybe creative writing. And the action is the specific thing you want done. Summarization, code generation, translating, editing an image, you name it.
Right. Can you give us a quick example of why separating domain and action is useful? Like, what's the practical upside?
Oh, it makes managing the policies so much easier. Imagine if you didn't separate them. You'd end up with these super specific, messy labels like summarize financial Q1 report for executives or generate Python code for data cleaning legal docs. Hundreds of them, probably. By separating them, if a user just vaguely asks for summarization, but the conversation context makes it clear they're talking about legal documents, the router can confidently pick the legal domain. The mapping T then knows which specific summarization model is best for legal text. It adds a layer of robustness, especially when queries aren't perfectly clear.
That flexibility sounds like a huge win for engineering teams, especially, with how fast models change these days.
Right.
So if I want to swap out, say, Claude 3 Opus for Claude 3.5 Sonnet for a specific task, I just edit that T mapping file, and I don't have to retrain the main 1.5B Router model at all.
Exactly right. That's the core practical advantage. You just update the mapping T, which is basically just a configuration setting, and the router itself doesn't need retraining. Plus, because those root policies are defined in natural language, the whole system becomes way more transparent and auditable. You can actually look at the logs and see, okay, this query came in, it matched the performance optimization policy, and that's why Model Z was chosen. You can actually understand the why behind the routing decision.
Okay, let's switch gears to the model itself. Arch Router. It's built on Qwen 2.5, known for being efficient, but still, it's only 1.5 billion parameters. That seems quite small compared to the giants it's routing between. What's the magic? What makes this little model so good at these complex routing choices?
Its strength really comes from its architecture. It's designed as a generative language model, not your typical fixed classifier. See, most existing routers are basically multi-class classifiers. They get a query, and they predict one of, say, 10 predefined policy IDs they were originally trained on. That's it. Arch Router, though, its job is to generate, literally write out the identifier text of the policy that best matches the input. And here's the kicker. They feed the full set of natural language policy descriptions into the model's input prompt every single time it makes a decision.
Whoa, hang on. That sounds really different. So you're saying the old classifier way baked the policy choices in when it was trained.
Yeah.
But this generative Arch Router reads the list of possible policies live from the prompt each time it runs.
Precisely. It doesn't see the policies as fixed, baked-in classes. It sees them as part of the context, right alongside the user's query and the conversation history. This means it can use all its pre-trained knowledge to understand both what the user is asking and the subtle meanings in the policy descriptions, all at the same time. So if you decide to add a brand new policy tomorrow, you just add its description to the list you feed into the prompt. The model can figure out how to use it immediately, at inference time, no retraining needed, just by reading the new definitions.
That makes it incredibly adaptive.
Yeah.
Okay, but making good decisions relies on good training data, right? Especially for handling messy, real-world conversations, not just clean examples. They use a pretty complex data pipeline, I heard. How do they build the training data to make the model so robust?
Oh yeah, that two-phase data creation pipeline was absolutely crucial. You need that to teach the model to handle ambiguity and, frankly, weird user behavior. So phase one was about generating clean, sort of perfect labeled conversations, getting the basics right. But phase two, that's where they injected the chaos, basically. They used targeted augmentation techniques to simulate real-world messiness. Things like irrelevance injection, deliberately throwing in off-topic comments, or even sneakily removing the correct policy from the list of options presented to the model, forcing it to generalize or rely on broader context. They also use policy modification, like adding options that sound really similar to the correct one, or deliberately misleading descriptions, making the decision much harder.
And what about the conversation flow itself? People change their minds, right?
Exactly. That's where scenario mixing came in. They actually stitch together dialogues with abrupt topic changes, or where the user starts asking for one thing and then just abandons it and asks for something else entirely. This forces the model to really track the user's intent over time through all the noise and shifts, remembering the history, not just reacting to the last few words.
Okay, so this intense training, this generative approach, what does it actually mean for performance? Can a specialized 1.5 billion parameter model, which is tiny compared to the models it's routing to, actually outperform the big guns like GPT-4o or Claude Sonnet when it comes to routing accuracy?
Empirically, yeah, it doesn't just compete, it actually comes out on top. In their evaluations, Arch Router got the highest overall routing score, hitting 93.17% accuracy, and get this. That score beat the aggregated average performance of the top proprietary models they tested, GPT-4o, Claude Sonnet 3.7, Gemini by a pretty significant margin, 7.71%.
Wow, 7.7% lead, that's substantial. I'm curious, where did this smaller model really pull ahead? Was it just better turn by turn?
Well, its turn-by-turn accuracy was definitely competitive, very strong. But where it truly shone, and this really validates that generative context-aware architecture we talked about, was on the longer range metrics. So looking at span-level accuracy, getting multiple consecutive turns right, and full conversation accuracy, Arch Router climbed to the very top. It hit 94.98% for span level and 88.48% for getting the entire conversation's routing correct. This gives us solid, measurable proof that it's significantly better at tracking that continuous user intent through complex, multi-turn dialogues compared to the larger, more general models being used as routers.
Okay, accuracy is great, fantastic even.
Yeah.
But, my practical side is kicking in. A 1.5B model, okay, it's smallish, but if it has to read the query, the whole chat history, and all those policy descriptions in the prompt every single time, surely it must be slow, right? We need speed for this to be useful in the real world. What about latency?
But that's where the structural design pays off big time. The efficiency is a huge practical win. ArchRouter turned out to be incredibly fast. It clocked in with a near-instant latency of just 51 milliseconds.
51 milliseconds. Seriously.
51 milliseconds. Now compare that to its closest competitor in terms of accuracy in their tests, which was Claude Sonnet 3.7. That one took 1,450 milliseconds on average.
Whoa. Okay, that's over a second and a half difference.
Exactly. Do the math, ArchRouter is demonstrably over 28 times faster. And the reason is pretty straightforward. ArchRouter is a compact, efficient, open-source model you can run locally or very close by. Those proprietary model benchmarks, they involve API calls. So you've got network latency, authentication overhead, whatever internal queuing or pre-processing they do, it all adds up massively. ArchRouter gives you the accuracy of a top-tier model, but with the speed of something incredibly lightweight and efficient.
Let's make this concrete. Can we look at the real-world impact of this subjective routing using that coding session case study they did? Tell us how ArchRouter actually handled ambiguous situations better than, say, a performance-first router like RouteLM.
Right. The coding case study is a great example. They pitted ArchRouter against RouteLM in this 11-turn back and forth about coding. The policies involved were things like code generation, bug fixing, and performance optimization. Now, RouteLM was set up to optimize for objective code quality scores like how good is the generated code based on some metric. ArchRouter, meanwhile, was using its preference-aligned approach, focusing on the user's intent. And there are a couple of moments that really highlighted the difference. In one turn, the user just says really vaguely, "This doesn't work. That's it. No keywords, super brief." ArchRouter, understanding the whole conversation was about fixing code, correctly routed this straight to the bug fixing policy, RouteLM. It completely whiffed. Because those 3 words didn't give it enough signal to predict a high objective quality score for any specific model, it basically punted and downgraded the request to some generic, weak model. It failed to grasp the context.
Okay, and there was another key moment.
Yes. Later on, the user says something like, "The code runs too slow. Any way you can simplify it to make it faster." Notice the subjective goal there, faster, simplify. It's about a desired outcome, efficiency, not just a technical function. ArchRouter correctly understood this subjective intent and mapped it right to the performance optimization policy. RouteLM failed again. It just couldn't align that subjective goal of make it faster with its internal metrics focused on objective code quality, so it misinterpreted the context.
So the big takeaway from that case study seems to be ArchRouter's generative approach lets it digest the entire conversation, including the natural language policy descriptions, and that allows it to pick up on nuance, follow-up intent, and subjective goals that a purely performance-based router, just optimizing for some score, completely misses.
Absolutely. And looking at how these models tend to fail is also pretty revealing. The error analysis showed some interesting patterns. ArchRouter, it turns out, is most likely to make a mistake right at the very beginning, on the first turn. If the initial query is really ambiguous, it might struggle. But here's the fascinating part. If ArchRouter gets turn 1 right, it's incredibly robust. It rarely fails later in the conversation. It seems to lock onto the user's intent and just stick with it.
Okay, and how did that compare to the errors from the big proprietary models, like the Claude model they tested?
Claude Sonnet 3.7 showed a very different pattern. Its errors were much more spread out across the entire conversation. Actually, its highest number of first failures occurred somewhere in the middle, around turn 3. This suggests that while maybe it handles that initial ambiguity slightly better sometimes, it's actually more prone to drifting off track or misinterpreting a subtle shift or follow-up after it's already started correctly. It reinforces that idea that ArchRouter really excels at maintaining focus on that continuous ongoing intent.
That is fascinating. A smaller model that's actually better at following the thread of a conversation than the huge competitors. Okay, let's wrap things up by talking limitations. Nothing's perfect. What are the known constraints or weaknesses of this whole preference-aligned approach that people need to keep in mind?
Yeah, definitely important. The framework is powerful, but its success hinges on a couple of things, really inherent to its design. First is policy precision. The router's accuracy, that impressive 93% score, depends directly on how well the users, the engineering team, define their policies. If the policy descriptions are vague or if they overlap too much.
Like if I made one policy analyze legal documents and another review contract clauses, is that too close?
That could definitely cause problems, yes. The router would likely struggle to reliably tell them apart based on typical user queries. The policies need to be distinct enough for the model to differentiate them clearly. Ambiguous policies will drag down the accuracy. The second constraint is what they call user model selection. Think about it. ArchRouter could do its job perfectly. It could analyze the query, understand the context, and route it flawlessly to the correct policy, say, generate highly creative marketing copy. But if the user has mapped that policy to a really weak, old, or maybe overly technical model that's terrible at creative writing, then the final output will still be bad. The system fails, even though the router itself was 100% correct. The ultimate success still depends on assigning the right tool, the LLM, to the right job, the policy.
Right, makes sense. So this whole deep dive really paints a picture of the future, doesn't it? We're moving away from just chasing objective scores and towards systems that actually try to align with what humans prefer with subjective needs.
Absolutely. And the structural advantage ArchRouter demonstrated is pretty undeniable. Getting that state-of-the-art routing accuracy from a compact 1.5B model and being over 28 times faster than the closest big competitor. It's not just interesting, that's potentially game-changing for actually deploying these kinds of multi-turn conversational AI systems in industry.
Yeah, the takeaway isn't just about speed, though that's huge. It's that this kind of flexible, human-centered alignment is probably going to be mandatory, not just a nice to have, for building truly effective production LLM systems going forward. You saw the power of defining intent clearly using that Domain-Action Taxonomy and the incredible flexibility you get from separating the policy choice from the final model assignment. So thinking about all this, what does it really mean for you, our listeners?
Well, this new approach kind of shifts the responsibility, doesn't it? It's less about tweaking the router model itself and more about how you, the user or the system designer, define your needs. Given that ArchRouter's accuracy lives and dies by how precise those user-defined policies are, it really pushes an important question onto you. In your own work, in your field, what are those crucial subjective criteria? Things like maybe the required technical depth or the desired level of abstraction in an explanation, or even specific output formatting that current benchmarks just completely fail to capture. And then the next step is, how would you write a clear, unambiguous policy description in natural language to capture that specific need so you could assign the absolute perfect model to it? Making that shift in thinking, focusing on explicitly defining preference. That really seems like the key to building more robust and genuinely useful AI systems.